Hi guys, today we will talk about a topic which I wanted to cover many months ago, and it talk about power electronics for energy harvesting. So basically, power electronics for energy harvesting is something that, okay, before explaining this, I will explain something like this. You have a source of energy source. It can be a solar source, it can be everything. And generally, the energy harvesting system has a step-up converter or step-up converter, batteries, and etc. Or you can even have solar energy. Then, for instance, a super cup like 1 farad and a step-up. Or you can have solar energy, which supplies, which in turn supplies a step up, which in turn charges a battery, and etc. 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 So in this case, we have a thermoelectric generator here, and then we have a step up transformer. Then inside of this, we have a switch which basically this is a DC-DC converter, a step-up DC-DC converter. It's basically a buck boost. And what it does do is you plug the battery here, okay, and you have a energy, solar energy, thermoelectric energy, whatever you want, coming from here. You step up this energy, and then this energy here is stored inside this capacitor. Now, you will have a load, okay? You will have a load. When there is an increase of the load, the output voltage will try to decrease as less as possible because there is the voltage stored in this capacitor here. What regards instead the auxiliary voltage Vox and VLDO, you can use these two voltages here to supply, for instance, a microcontroller, because of course your system will it has to be monitored and controlled. You will have, for instance, here NTC. You will have also dividers here, which in turn will go to the microcontroller instead. So there will be, of course, the so-called logic. You need the input voltage, the input current, you need the output voltage, you need also the output current, you need the temperatures, T1, T2, and the temperature of this, T3. You need also to read the store voltage VStore. You need also to read the voltage Vox. You need also to read everything. And what you do is to typically to take a divider and a capacitor as low pass filter here. You design the divider so that the voltage Vin is scaled to the 3.3 volts, or the voltage of your basically ADC. To calculate the resolution of what you can read, remember that the formula is the resolution, which is the LSB, is equal to the maximum voltage of your ADC over 2 over bit. And you will discover that this value can be like 1 millivolt, like, I don't know, 1 millivolt, 500 microvolts, and etc. So let's design this system here, and let's use also the two capacitor C1 and C2. C1 and C2 are used for the charge pump inside this circuit here. Whenever you have to choose a system like this, remember that what you have to look is what kind of energy you can harvest. In this case, we have thermal energy. How much auxiliary voltage and how much voltage, clamped voltage there is. And of course, if there is the battery use indicator, bet off. The IQ is the quiescent current. So basically is the current drained also when the system is on. This is extremely crucial in energy harvesting system. I will underline this because this current you cannot reduce this current whatsoever. In a system in which, for instance, there is a supercap, so you have the battery, and here there is connected with a resistor, there is a supercapacitor with, I don't know, 1 farad. This supercapacitor will drain like 1 microamps, even 10 microamps of IQ. Now, it may seem slow, it may seem low, but if you multiply this current for 10 years, you will discover that a lot of charge will be drained by the battery. So if your aim is to make your battery live as much as possible, the quiescent current is one of the crucial parameter of design. In this case, we have 80 nanoampere when energy harvesting and 6 microampere no energy harvesting. So it's not so much, but this has to be minimized as much as possible. In the next lines of the datasheet, it explains shortly what it does. Using a small step transformer, the LTC provides a complete power management solution for a typical wireless sensor application that operates from a primary battery. The 2.2 LDO can be used to power an external microprocessor. Like I said before, you will need a microprocessor in order to, of course, study all these voltages that you need. The LTC seamlessly transitions from battery power to harvest power whenever harvest energy is available, extending the life of the battery. The bat-off indicator can be used to track battery usage. There are also some other controllers out there which estimate the SOC. The SOC is the state of charge. It basically tells how much charge is left in the battery, and with some precise algorithm, you can estimate the life of the battery. Here you have basically the pins, but I already explained to you. C1 and C2 are the input of C1 and is the input to the charge pump, and C2 is the input to the N-channel gate drive circuit. Now we can open LTSPICE and we can search for this controller, for this LTC 3107. Ultra low voltage energy harvester and primary battery life extender. So it has both the energy harvester and also the battery life extender because of the V cap. So now we will suppose that we have the thermoelectric source, which will be 50 millivolts, for instance. These source translated in voltage are very low, generally speaking, okay? And we will put a series resistor, the milli, and a capacitor in the input of a very big capacitor, like 100 micro. This will be our input voltage. Now we have to design the step-up transformer with the ratio 1/100. We can use 2 inductances like this. I need some more space. K, L1, L2 equal to 1. Okay. This has to be connected with 2 capacitors. Like this. Now this is grounded. And these 2 capacitors are suggested by the datasheet. 1 nanofarad and 330 picofarad. Now, in order to in order for this transformer to work, we have to first set the ratio 5.7 micro one side and 75 milli to the other side, because the ratio is determined by a square root, if you do remember. This has to be connected to the switch voltage because it has to operate. The switch has to charge and discharge the transformer. The ground creates a path to ground, which is also to connect to basically all of this. Now, for the auxiliary power and store, we can just use 10 microfarad for both of them. 10 microfarad grounded. Then we can use the V also a capacitor for the VLDO. This is the barrier. And then the output voltage. We can use a capacitor or 40 or 50 micro. And we can put a resistive load of we can say R equals to if the time is greater than 800 milliseconds, then the value is 50k, otherwise 36k. This will be the node of the output voltage, the out. This will be the node of the battery off, the bat off. This is the node of restore. And the battery is generally represented like a battery of 3.6 volts, a series resistor, which sometimes are also quite high. 1 ohm is enough, okay, but let's put just 1 ohm like this. And parallel capacitor of a parallel capacitor of I don't know, 20 microfarad, 30 microfarad. What does the datasheet says? 10 microfarad, yes, it is enough. Naturally, this will be grounded. And this is the node VBAT. So we have the input voltage, the battery voltage, the output voltage. Everything is ready, except for the ground. Okay, now I have the ground. So everything is ready. Let's put a title. Power electronics for energy harvesting systems. Okay, let's reduce some space here because we don't need it. Okay. Now let's run the simulation for 1 second, and we should be good. We need also parallel resistance of 500k. Okay, I think that everything is in order. Let me check. Because yes, we need also the parallel resistor of this because it is very low. VLDO, and the load is here. Okay, I think that we can go. Okay. So we want to monitor the VStore. As you can see, the VStore after some time is starting to increase the voltage because it is starting to store the voltage. As you can see, VStore is increasing after 100 milliseconds because we have the source, the thermoelectric source, which is charging our system. And when it is exceeding the energy, then it will start to increase. Because I assume that the battery is fully charged, so naturally it starts to increase after a while. Then we also want to monitor the battery voltage, VBAT, which is constant to 3.6. We also want to monitor the output voltage, and we also want to monitor the load. Okay, now something is happening. As you can see, exactly as we planned, the load is increasing after 0.8 second, but the output voltage is not decreasing so much. I'd say that is not decreasing at all, because what is decreasing here is the store voltage. In this way, the battery has not to give any current, and we can see here by just putting the current here. You see that even though there is an increase of voltage, an increase of load voltage, there is not an increase of load battery. As you can see, I have just 0.4 nanoamps before and also later. So there is no current coming from the battery at this point. The output voltage instead goes from 3.75 to nothing, 3.75. So the output voltage remains the same. The load instead goes from 100 microamps to 200.5 microamperes. But there is no change in the battery voltage and the output voltage as well. What it does change instead is the store voltage, which goes from 5.4.3 to 3.89, which means that some current it has to be drained by this capacitor here. Let's see if this is true. And as you can see, there is an increase of current of IC5. Naturally, this current has some switching noise, some switching problems, but as you can see, there is an increasing in the frequency during this interval here. So basically, the energy is drained from the V-store and the life of the battery is prolonged instead. This is an example of how power electronics can work also for harvesting energy system. I think that I can end the video here. I hope that you enjoyed and see you in the next video.